The technical summit will focus on the pilots. Preceding the pilots, we will just present to you what the technology of seasonal thermal storage is all about. That will pave the way for the more technical details that each of the partners that are implementing pilots will present. My name is Shadi Najjar. I am the project coordinator of STORM from the American University of Beirut. AUB is the lead partner on STORM. And we have 6 other partners from different areas, different countries in the Mediterranean that will be also implementing this project with us. The project is funded by the EU under the Interreg NEXT MED Programme, and we would like to acknowledge the funding and the support of the Interreg NEXT MED staff, Joint Secretariat, Managing Authority as we implement this project. STORM is a project that has a budget of $2.7 million. It is funded 89% by the EU and the others are co-funded by the actual partners. The project is for 3 years, 36 months, and we are already in month 8. So we started last August. The whole spirit of STORM is to try to show what the potential of seasonal thermal energy storage is in the Mediterranean region. And the reason why this is important is that the Mediterranean has a challenge related to greenhouse gas emissions, as in any other area of the world, due to the use of fossil fuels in the different sectors of the industry. The specific concentration of STORM is on cooling and heating of buildings. And if you look at the statistics related to greenhouse gas emissions in the building sector in particular, you could see that the different countries that are bordering the Mediterranean have a major contribution. The global average, if you just want to have a feel of the numbers, for the greenhouse gas emissions is around 0.44 tons of CO2 per capita. The EU average is 1. And you can see here that many countries in the EU, in the Mediterranean, are at the higher upper bound of the emissions. There are other countries that have less emissions. But the idea is to see from where these emissions are coming. And if you only take space heating of buildings, you would see that the source of energy that is used to do space heating is generally from fossil fuels, even with all the effort that has been done in the last 20 years to support the use of renewable energy. So if you look at the statistics, there's only 33% of the demand for space heating that is being replenished by renewables in the EU. If you look at Lebanon, it's even worse. I mean, it's only 90% of the sources of energy for space heating is fossil fuels, whether it's diesel, whether it's gas, combination, electricity, etc. So this is the challenge. When it comes to the potential of the Mediterranean has a potential for harnessing solar energy to try to solve this problem. And again, the opportunity comes because of the location of the Mediterranean and its solar potential. This chart just shows for the Mediterranean countries the annual global horizontal irradiation. It's just an indication of how much availability there is for sunlight and the ability to transfer that into solar energy. And you could see that all the countries that are bordering the Mediterranean have a higher than average solar potential in terms of irradiation. So that's where we need to focus on. Now, how do we harness that, or how do we make use of this advantage? There is technology right now that allows us to use basically sunlight to change it to energy. The 2 most common technologies that are available out there are either solar PV, and this is for generating electricity, or solar thermal, and this is basically a technology that allows us to heat a certain fluid. It could be water, a mixture of water and other material, to get thermal energy and then try to make use of it. All of us have seen these on roofs, whether the PVs or the solar collectors. Now, the problem here is that when we talk about space heating in particular, as an example, when we need space heating, it's in the months that the sun is not there, or it is basically less available. and the irradiation is at its lowest. So there is really a need to be innovative when it comes to figuring out how to use the energy solar potential that is in the Mediterranean. And the thing that comes to mind to try to match this mismatch between the availability of the sun and the need for the heat is by trying to store that energy. So try to collect it in the months where it is available, put it in a place that will hopefully keep it there as much as we can, and then use it when the winter comes to try to provide space heating to buildings. So this is the idea of seasonal thermal energy storage. The question becomes, where do you put that heat? And here also there are alternatives. One of the alternatives is to put that heat in the ground and store it in the ground, natural soil, natural rock. And in this technology, now we're talking about having to drill in the ground to be able to create some kind of heat exchangers that would allow us to transfer the heat from the fluid that is coming from the solar collectors and try to transfer that heat to the ground. In a minute, I will go into the technology a little bit more and explain what is happening. The other way to store that heat is by creating artificial tanks. So we can create a tank that is made of steel or concrete. It could be above ground, it could be underground. This is a manufactured tank, not a natural soil or rock like the borehole technology. And then you have to insulate that tank and then try to also store that heat in it and hope that it will remain there for the season of charging until you reach the winter where you want to discharge it. There are so many permutations to these technologies. We will focus on a couple today, and I will show a couple of case histories before we start. Now, what is the technology? The technology, as I said, in a very simple step-by-step procedure. You have to use some kind of solar collectors to be able to get the energy from the sun. There are so many technologies out there. There are flat plate collectors, evacuated tube collectors. Doesn't matter what it is. The idea is that you get a certain meter square of these collectors, and then you circulate a fluid through them. That fluid will increase in temperature to values hopefully in the order of 80 degrees, 90 degrees. And then you take that hot fluid, and for the case of boreholes, you drill boreholes in the ground, maybe up to 30 meters, 50 meters, 100 meters, depending on the application. And in those holes in the ground, you put tubes. And these tubes basically allow you to circulate the hot water through a pump. And if you circulate at the right flow rate, you will give enough time for that heat that was collected to enter into the rock or the soil. And by the end of the charging season, you could end up with the rock in that location have temperatures in the order of 40, 50 degrees, depending on the application. Now, unfortunately, there's no way until now to keep that heat into the ground. So by the time you reach winter where you're going to use it, a big portion of that heat will have dissipated into the rocks that are beyond this borehole thermal energy storage system. So there are losses, of course, but still what remains is enough to have an impact. And it's all renewable energy, pure renewable energy that you can use for space heating. So the next step, after you have charged the ground up to 50 degrees, let's say, when the winter comes, you circulate cold water now in the ground. As this cold water circulates, it gets heated up, and you take it, and usually you pass it through a buffer tank first, and then you take it to the building. So if the building is now using diesel oil to heat water, to heat the radiators or the underfloor tubes, now you use hot water that's coming naturally from the ground, 100% renewable, to heat your homes. Same technology, same everything, except that the source of the heat is not anymore burning fossil fuels. It's heat that was collected back in the summer and that remained in the ground until the winter season. Now, the problem here is a lot of the heating systems in buildings require temperatures that are in the order of 60 or 70 degrees. And in this case, if your ground is at 40 or 50 degrees, it will not give you the working temperature. And this is why you might need a heat pump. And this is an additional cost, additional need for electricity, but these heat pumps are very efficient, and then they can raise the temperature to whatever you need in the building with minimal cost and minimal use of electricity. This is the system in a nutshell. It can change, there are permutations to it, but at the end of the day, this is what seasonal thermal storage is all about. The last part of this picture shows you the tubes that enter into the boreholes, bringing in hot water and then coming out a little bit cooler. So I will share with you 3 case histories where this has been used efficiently, and these come from 2007 all the way to 2025. The technology, as you will see, is improving. People are doing tweaks to make it even more efficient. The cases, one of them is in Canada, the Drake Landing. The other one is in Norway, the Fjell School. And the last one is in Slovenia. So let me start with the one in Canada. This is one of the most famous case histories where this technology was really demonstrated. This case involves 52 homes in Lake Dranking in Canada. These homes are in the most severe winter conditions in the world, sub-0 degrees throughout the winter. In this particular case, there were around 2,300 meters square of solar collectors that were installed on the parking garages of all these homes. And these basically had the function of collecting hot water. The project basically involved harnessing all this energy and taking it and putting it in the ground through 144 boreholes that were drilled to 35 meters in the ground. One of the largest borehole systems at that time. During the charging season, which is the summer and part of the spring, 700 megawatt hours of thermal energy were harnessed and pushed into the ground and stored. By the end of the charging season and during the extraction, only 300 megawatt hour were able to be extracted from the ground, giving this system an efficiency of around 35%. So we were able to collect 700,000, but at the end of the season, we were only able to use, they were only able to use 300 or 350. So this tells you something about the efficiency of this whole system as it is in its existing practice. These are some pictures. These are the solar collectors that were installed on the parking garages. And this is a picture of the borehole system. It's one of the nicest pictures that you see in the published literature. It's just a large area in which these 100 plus boreholes were drilled. And of course, all the tubing that comes with them that connects all the system together. We're very excited that we're going to be implementing as part of STORM 2 of these systems, one in Beirut and the other in Palermo. And we will get the chance to talk about them today in details. The team will be presenting them soon. In a nutshell, basically this picture shows you the whole system. You can see the solar collectors on the garages. You can see how the hot water is gathered and taken to a energy center where there are buffer tanks. There, the control of these temperatures is done, the water is done, and the next step is to take the hot water into the borehole system and during the winter take it back to the houses. One of the key secrets for having this system work efficiently if you have already a district heating system existing in the region. And this is not present in many of the Mediterranean countries. This is present in Europe, in all Europe almost. The presence of a district heating system allows you to connect and plug to this system your borehole thermal energy storage. So this is a challenge when you're dealing with an area that doesn't have district heating and if you want to really distribute the heat to a lot of buildings. Some numbers, and I think I need my eyeglasses to see them here. Maybe I can see them from there. So the heat storage volume, we call it the storage volume in terms of, you can think about it as if it's a tank, is in this particular case history 35,000 meters cube. So the rock that was heated up to 50, 60 degrees in this case is 35,000 meters cube. This is how you get your 700 megawatt hour. I mean, this is not a small number. The energy stored in the BTES is 700 megawatt hour, as I mentioned, and the extraction efficiency was 35%. So let me take you to the newer one. This is a case history in Fjell in Norway. If you look at this system, it's a school, and this gives us an example of the applications of this system. So it's a full-scale school. In this particular application, the system includes solar collectors also, but not as a main primary component. These are just to support the system, 125 meters square. we have 1,000 meters square of PV solar panels. But the interesting thing is that they did not use the solar panels to provide electricity to the school. The solar panels here in this case were installed only to operate a heat pump using renewable electricity. And the heat pump had the objective of producing the hot water. So here we're relying a lot on PV electricity to heat water through the heat pump and then get the hot water and store it in the ground, 100 boreholes, again, 50 meters deep. This is a typical practical case history that can be applied anywhere. Some statistics also, the facility itself is 8,000 meters square. The solar panels, if you add the two types together, 1,125. And this system was able to produce 800 megawatt hours, so very similar to the case of Canada. And out of this, they were able to extract 350, giving this around percentage in terms of efficiency, around 40–45%. So here the change is that there is a need for a heat pump. In the case of Canada, they didn't use the heat pump. They just relied on the temperature that's coming out of the ground. The final case history, so that I don't take a lot of time, is the most recent is it's in Slovenia. It seems the trend now in these systems is to move to a heat pump as a source for the hot water. It seems that calculations are showing that this could be the most efficient system. So here we have 400 meters square of solar collectors, 2 air-to-water heat pumps that are providing the hot water to be able to charge 55 boreholes, 27 meters deep. So the scale of these things is starting to become smaller and more targeted towards certain structures. Previously, it was bigger scale for district heating for areas. So this is what we're aiming for in STORM, to test these systems in a decentralized systems that could be at the order of a villa or a house or a 10-story building or a 5-story building. So in this case, the facility is 2,500 meters square. The solar collectors are 400. And this system charges 160 megawatt hours per year. And you can extract out of it 80, mentioning 50% efficiency. This is one of the cases with the highest efficiency. This picture shows you again what the system entails. It's about drilling the boreholes, connecting them with a network of pipes properly, and in this case, adding a heat pump that will be the source of the charge of the system. The nice thing that I like about this case history, it is very well documented and it has live data. So now if you want to research the Dewisoft Industrial Facility, BTES, you go to their website and you can go and look at what is happening right now in terms of energy entering into the system, leaving the system, the temperature of the whole boreholes, the temperature, the flow, etc. So if you're interested in this, you can check it out, and it's really interesting to look at it. So I just wanted to give you a feel of what these systems are and how relevant they are. I mean, these are recent technologies. A lot of startups are coming up trying to say that we do this and basically advertising this as businesses. And perhaps the most one that gained attention, and now I'm moving to the second technology, which is the tanks that people create outside the ground, is the one that you see here. This is a company in Finland, and they are claiming that they can produce heat up to 400 degrees through like a product. They sell it to you. They tell you, okay, what do you want? You tell them, I want a 10 megawatt facility that will give you 10 megawatt of heat during the winter. And so they provide the system to you as a product. And what they use in this case is an insulated tank that can be in different sizes. They fill it with sand. They're using sand as the storage material. And they're using electricity to heat the sand up to temperatures in the order of 600 degrees. So here we're talking about a totally different application. The ones that we were talking about were water, hot water. Now we're going up to 600 degrees. You're talking about sand, no limit on the temperature that sand can take. And when you reach 600 degrees, now you can provide a service that is really very highly efficient, and it can provide you with temperatures that are at a very, very high level. And you can even do electricity production with this using a steam engine or any other technology. So I'm not going to talk more about the systems, and I don't have time to talk about other case histories for tanks, but they are there. And we have our partner in Jordan that is trying the technology of a tank in one of the pilots. So overall, we have 3 pilots that are being implemented from scratch in Storm. In terms of cost, I think the question that always is the one that is hidden, we don't want to talk about it, is cost. These systems still cost a lot of money, especially if we're doing them at a decentralized, small-scale fashion. So when you go big, the cost go down in terms of cost per meter cube of, let's say, water at a certain temperature. So the trick now is that the technology is advancing a lot, and the cost will surely, with time, become more and more, let's say, reasonable. But still, these systems can have a return period on investment that could be reasonable, given the added benefit to the environment. But still, cost is the really thing that is negative at this point in these technologies. So to wrap up, why are these technologies not yet available in our area? There are many reasons. First of all, there's not enough data that show their efficiency and how good they are. The likelihood of success when there is no district heating system network is relatively low, so you have to deal with this as a constraint. Economic feasibility is questionable, and we have limited knowledge about the behavior of soils and rocks, natural soils. It's a complicated technical problem to really model what's going to happen in the ground when you start heat transfer using these systems. So there is a need for research on decentralized small-scale BTES and TES systems, and this is what STORM is trying to do. The expected result from STORM is to have, at the end, an enhanced visibility and access to these innovative, cost-effective, tested solutions. We want to test them ourselves to see how they work in the small scale, and eventually to be able to tell people about their use, how good they are, how bad they are, where they are efficient, where they're not, based on our own experiments and research. The objectives of STORM, if I want to, without going into the details, we want to raise awareness of this technology in the Mediterranean. We want to encourage its adoption. We want to demonstrate its effectiveness, and we want to develop some kind of long-term strategies for their use. This is my last slide. As I said, STORM has 6 partners in it. AUB is managing and coordinating the project, and we are leading the communication part of it. Our partners in KIM-BCN are leading a digital platform that is part of STORM, and they will talk about it today. Our partners at the University of Campania are leading Work Package 4, which is focused on design and coming up with practical design toolkits that will help people use this system, which is unknown to many. Our partners at the University of Palermo are leading the Work Package on the pilots. And we have our partners in Jordan that will lead Work Package 6, which will focus on policies and strategies. Of course, AUB Mediterranean is the 5th partner, and we have Lebanese Center of Energy Conservation in Lebanon, LCEC, as our final partner. So with that, I end my presentation, and I think we can take quick questions if there is before we move to the next part. Yes? Yes, the difference is that for geothermal energy, you are not actively collecting thermal or other sources of energy and forcing it to be in the ground. Geothermal, you make use of the fact that the temperature of the ground is stable all year, and you try to take that and you make use of the delta T, correct. Here we are actively increasing the temperature in the ground to values that allow us to use it later on.